My name is Steve Twa. I'm a researcher and engineer in the area of audio signal processing and music information retrieval. I like to play the violin. I'm a violinist and the concertmaster with the San Francisco Civic Symphony, an amateur community orchestra in San Francisco. In college, I studied electrical and computer engineering in the areas of signal processing and machine learning, and I did some research in music information retrieval as well as digital image forensics. What is research in academia like? There are three main parties. There's the students, there are the professors, and there are the funding agencies. And just like any business, it's a system, a cycle, where each part depends upon one another, and each party depends upon the other to keep the wheels turning. The students do the work, the professors guide the vision, and write the grant proposals from the funding agencies, which allow the students to do the work. You know, I often think that it's very similar to, for example, Congress. In Congress, just like politicians whose decisions are guided by the next election, in academics, researchers are often guided by the next conference and the next journal paper. While, yes, there is some long-term direction involved, the quick wins allow those small incremental progresses to accumulate, and so we can truly be dwarves standing upon the shoulders of giants. Unfortunately, sometimes that does lead to some myopic short-term thinking where what gets developed in academia is not truly what either industry or perhaps the world may really need. I think those best departments are those which do reconcile the two worlds, do research that is truly needed by industry, while taking some risks just enough to be sufficiently different, novel, and useful. What are interesting technical challenges to me are converting results from research into industry, into the real world. Often, when you look at a conference paper, you'll see some results, and those results will be very tantalizing. But what lies beneath the paper is a system that is what I like to call research quality. It's not industrial strength quality. What is needed to go from research quality to industrial strength quality? Well, there's a lot. When you're now working for an enterprise, which is making a product that customers spend money on, you need to make sure that all of these assumptions are met and all of these loopholes are closed. That in all of the possible edge cases you can possibly think of, your product works smoothly, seamlessly, and without fail. One example in industry where I was able to apply a research concept to a product that we were trying to develop came when we were developing a search engine of sorts. And as with any search engine, retrieval time is a very important characteristic. A user isn't going to sit around for even 5 seconds waiting for a result. You want that to come as quickly as possible. Now, when you're developing a search engine, the brute force method of returning results is to look at every possible item that exists in the database, find which one scores the best, and return the top end results. Obviously, that will take a long time. You don't have the luxury of computing scores between your query and every existing item in the database. So there is this one particular algorithm called locality-sensitive hashing, which we were able to successfully implement at a very basic level, certainly not to the level of sophistication that you would read in research papers, but just the core elements. And that small addition alone was able to significantly reduce our retrieval time by orders of magnitude. I think the lesson from that little example is that there are a lot of algorithms out there in the papers, and they have varying levels of sophistication. Some of them are in their infancy, some of them are 30 years old. Often you don't need the most recent algorithm and the hottest thing that was just released yesterday. You just need something that works that's better than zero. And a lot of products today in industry are at zero, depending whatever problem that is trying to be solved at that point. If you're just a little bit better than that, then you have a significant competitive advantage.